So far in our discussion of fluids, we've focused only on fluid statics, fluids that are not moving. But there are examples of fluids flowing all around us, whether it be wind blowing or a river running. Now it's time to turn our attention then to moving fluids, or fluid dynamics. Here we go. To begin, we have to understand that fluid flow is a complex subject that's still not entirely understood. So in order to avoid difficulties, we're going to use a simplified model of an ideal fluid. And this model can be expressed in 3 assumptions about the fluid. First, the fluid is incompressible. This is a pretty good assumption for liquids, as we saw in class, but it also holds up well for moving gases like air. Second, the flow is steady. And third, the fluid is non-viscous, which means viscosity is resistance to flow in a fluid. So viscosity is analogous to friction for solids. So basically we're saying we're going to assume little internal friction in our moving fluids. Now there's 2 types of flow. There's laminar flow and turbulent flow. Laminar flow is the motion of a fluid in which every particle in that fluid follows the same path as that followed by previous particles. Basically, it means that the particles in the fluid are traveling in smooth lines, one right after another. We can represent laminar flow by drawing what are called streamlines around an object. They're just example paths that the fluid particles are traveling along. Now, streamlines never cross. Fluid particle velocity is tangent to that streamline, and the speed is higher where the streamlines are closer together. Turbulent flow occurs along high flow rates when the fluid is moving past irregular shapes. So turbulent flow, you'll see if you ever look at a stream as it runs by rocks, it'll often be smooth laminar flow in front of the rocks and become turbulent behind the rock. Now, as we said in our assumption about the fluids we'll be looking at, the flow is going to be steady. So all of the flow that we're going to look at will be this laminar flow. So let's start by talking about what's called volume flow rate, or often called rate of flow. The rate of flow is simply the volume of fluid that passes a certain cross-section in a given time. It's just simply the rate at which a volume of fluid flows through a closed container, like a pipe or something. So here, for example, this is a picture of a pipe, okay? So it's got a wider diameter pipe here than here. So we have this pipe makes a constriction. So let's look at just this section of it here. From one point to another, we have a length of that pipe. And then we have a cross-sectional area here. Since volume flow rate is simply the rate at which a volume of fluid flows through that pipe, we can say mathematically that it's this volume over time. So this V stands for volume here. Well, the volume of a pipe is basically a cylinder. Volume of a cylinder is pi r squared times the length over time. Well, if we're looking over here at a cross-sectional area of that pipe, a cross-sectional area is simply a circle. So area of a circle is pi r squared. So we can have that cross-sectional area times that length of pipe over time. Well, what's this length over time? Length is nothing more than a distance, right? So what is distance over time? It's velocity. So what we end up with volume flow rate is simply the velocity of the fluid times the cross-sectional area of the pipe. Now the water that enters the hose at any given time has to equal the water that leaves the hose in the same amount of time. Which makes sense, right? We can't push more water in than we get out, right? And we can't get more water out of a pipe than what we push in. So the flow rate has to remain constant no matter what happens to the size of the hose. So even in this constriction here, the flow rate has to remain constant in both sides. So what does that mean as this area changes for the velocity? In other words, for a fluid flowing through a pipe, if the diameter of the pipe changes, what happens to the speed of the fluid? No matter what happens to the pipe, right, the volume of fluid that goes into that pipe has to be the same volume of fluid that comes out. If you squeeze a toothpaste tube, the volume of toothpaste that emerges matches the amount by which you reduce the volume of the tube. The same is true for a fluid in a tube. Fluid is neither created nor destroyed within that tube. It can't be stored. So if the volume enters the tube during some time interval, then an equal volume of fluid has to leave the tube. We can model this with the equation of continuity, where we've got the velocity of the fluid times the cross-sectional area at one point has got to equal the volume times the cross-sectional area at a second point. The result of this then, the consequence is that the flow is faster in narrower parts of a tube and it's slower in wider parts of a tube. You experience this every time you use a garden hose with a nozzle on it. The narrower opening of the nozzle makes the water exit at a faster speed. You can also see this every time you turn on a faucet too, right? The water that flows out of a faucet picks up speed as it falls. As a result, the flow tube tapers to a smaller diameter further down. So as an increasing speed causes that diameter to decrease. So the main point here is that as a fluid goes into a constriction, it's got to speed up so the same volume of fluid can get through that constriction as what moves behind it. Now, this equation of continuity describes a moving fluid. It tells us what it does, but it doesn't tell us anything about why it does it. To understand the dynamics then of a moving fluid, let's take a look at this picture here where we've got a pipe that constricts into a narrower opening. Okay? We know from the continuity equation that this volume of fluid has got to equal this volume of fluid, so we're going to have an increased speed in here. The question is, why do we have an increased speed? Back here, that fluid is flowing at a constant speed here, and here it's faster. That means in here, it's got to accelerate. Well, in order to have any kind of acceleration, Newton's second law tells us there must be a force acting. Now, as long as we're assuming that this is a non-viscous fluid, we can look at it this way. So, if there is a force acting, we have an acceleration, there's got to be a force acting. That force has got to be pushing that in that direction of that acceleration. Where's that force coming from? Well, it's coming from the water pressure, okay? So there's got to be greater pressure on one side of that constriction than there is on the other side. So what we've got is a pressure difference. So we're going to get a net force on the fluid causing it to change speed if and only if there's a pressure difference between the two sides of that constriction. We call this pressure difference a pressure gradient. Okay, and it leads us to be able to talk about what's called the Venturi effect. Now, because an ideal fluid accelerates wherever there's a pressure gradient, the Venturi effect says that pressure changes are accompanied by changes in velocity. So here is pictured a pipe, and it's got these three pipes coming up out of it, right? So if this liquid that's in these pipes is in static equilibrium, if it's in hydrostatic equilibrium, right, the Pascal's principle will tell us that the liquid will rise to the same point in all three of those openings there. If, however, we cause that fluid to flow through here, there's greater pressure here than there is in this constriction, so that the fluid increases velocity here. That increased velocity will result in a lower pressure in that higher velocity fluid. And there will be greater pressure on either side, which would cause that liquid then to drop in that middle tube. This is called Bernoulli's principle then. Bernoulli's principle says that when the speed of a liquid increases, its internal pressure decreases. This doesn't apply to just liquids, of course. It applies to all fluids. So when the speed of a fluid increases, the internal pressure of that fluid decreases. Moving fluid means lower pressure. This is a consequence of the conservation of energy, and it's something we're going to look into in more detail in the next video. See you then.